Today's topic is curl and divergence. Like, what are curl and divergence? Okay, so far in 3D, how do we take a derivative with respect to space variable? For example, quick review, if we have function x, y, z, right? Do you remember gradient? If you take gradient of a scalar function, then it's just partial f with respect to x, and then attach I vector, and then partial f with respect to y, and attach j vector, and then partial f with respect to z, and attach k vector, right? That's gradient. Well then, what does the second derivative look like? Or, if you have a vector field, let's just call this thingy vector f. Not enough space. Why do I never give vector f, x, y, z? That's ugly z, isn't it? X, y, z. If you have a vector field like that, how do you take a derivative of that? Okay. So that is today's topic. Okay. So that was just a quick review. So I'm not going to really have it that way, although at the end I will shortly introduce the second derivative. So say there is a vector field f, which is function of x, y, and z, like your tornado, and this thing has p, x, y, and z, with I vector generally, plus, I'm gonna shove these things out of the way. We'll look at it in a mid-minute. Q, and then we have function of x, y, and z, and then, not comma, j vector, and then we have R, some function of x, y, and z. And prime example of this is your tornado, right? You remember x component, y component, and z component to put it together. Okay, if you have this, how do you take a derivative of this? So this is a derivative of vector field now, right? Which can potentially be the derivative, second derivative of this. But what I mean by second derivative is one of the two. Okay, so let's just take a general general derivative of vector field. There's something called the curl, and there's something called divergence. Okay, just name suggests something, right? So I have two different vector fields. I have this looking thingy, your tornado looking thingy, some swirly thing going on, and then I have this thingy. Can you see this? Right. Can you see it, or you want me to take out the graphic calculator to give you this? Okay, assuming you can see it. Which one measures which? The name should suggest one measures one and the other one measures the other, right? Which one do you think will give you a positive number? You would think this will measure curl. I mean, the curl will measure something like this, and divergence will measure something like this. You would think, because this is a diverging field, and this is curling field, like what you started your tornado with this. Okay, so that's what these things are, and let's see if it really does what it's supposed to do. But I'm gonna write down the formula first. Push this down a little bit. So curl is done this way. It is your del operator cross product with your vector field. Okay, and that of course is done with I, j, k, partial x, partial y, and partial C with your P, Q, R. Good. So far with me. And then divergence is, can you take a guess? It's a dot product of the two. So if you have vector field PQR, it just means this and then dot product, you add them up with Y and then your R with respect to Z. And that's how you take the derivative with the of vector field. Because these are vectors already, so there are two different ways to do this. You know what I'm saying? Because this del operator itself is a vector. Okay, many mathematicians, this is more of a physics notation. Many mathematicians don't like this, especially this notation, but we'll use it anyway. Okay, so back to this field, okay? So suppose we have a couple of fields like this. We're going to write this field down. And this is easier, this vector field right there, F, here is X, I vector plus Y, J vector plus Z, K vector. Do you see that? Do you see that's diverging field? Can you feel it after doing tornado? Okay, and this, you want me to call it different vector field other than F? Or is that fine? Y, I vector minus X, J vector plus 0, K vector. So this gives you counterclockwise rotation, doesn't it? Okay, we are going to take divergence and curl of both of these. Okay, let's take divergence first. So if I take dot product of this, it just means partial y over partial x plus or minus partial x over partial y plus 0. And that whole thing is 0 now, isn't it? Is that surprise or is that expected from the shape of the vector field? And this one, if you take a dot product, then this is partial x over partial x plus partial y over partial y plus partial z over partial z, so you get 3. So this thingy measures the divergence, if there is any. If this is just swirling vector field, there's no diverging thing any. If you throw in some kind of particle dust in here, it will just swirl around and it will not diverge. So divergence is 0. That makes perfect sense to you? Okay. Now we'll take curl of both of these. So let's take curl of this one, cross product. Okay. So here we have I, J, K, and partial with respect to X, with respect to Y, and with respect to Z. And with that, PQR, so we take Y here, negative X here, and 0 here. And let's see what this thing gives us. Okay, with I vector, this and this is 0. With J, this and this is 0 again. So K is the only thing that survives. And K, you have 1, right? Do you see that? This is negative 1 minus 1. So we have negative 2. You know what I'm saying? Say something. What is wrong with you kids today? Good. Wait a minute. Is this clockwise or not counterclockwise rotation? This thing should have been a counterclockwise rotation. Let's think. I and then X, J. Yeah, this is counterclockwise rotation. You feel it? And then now this thing tells you this is negative curl, meaning counterclockwise rotation. You get it? Huh. Okay, so it measures something swirling around. And we'll take a curl of this vector field now. So del cross F. Same way. So we have I, J, and K. And then partial with respect to X, Y, Z, and then we would have X, Y, and Z like that. Let's see what this thing gives us. So with I, that's 0. With the J, that's 0. And K, that's 0, right? So we have 0 vector. Because there is no curl going on. Nothing is rotating. You know what I'm saying? So that gives us 0. Okay, so curl. Divergence is a lot easier to feel than curl, okay? But a little thing about curl that I have to mention is this. Say there's a vector field that looks like this. At this point, is there a curl? If you measure curl, will you get something positive, something negative, or 0? Some brave souls speak up. What you're imagining is if you release this little tiny flower-looking thingy, of course it's going to move that way, right? But will it rotate as it moves, or will it just move? Is my question. Which way is it? Awkward silence.
I would just move.
Okay, let's just look at the differential. This side is being pushed tiny bit. Think of it as a wind. There's a stronger wind, this on top than the bottom. So do you see this where, you know what I'm saying? It'll move but rotate at the same time. So curl does not have to be at the center of the tornado. You know what I'm saying? If you have this thingy in your tornado, it'll spiral up like that, right? But it'll rotate by itself. So there's a curl everywhere. You know what I'm saying? So you have to be able to feel this. So this thing will give you negative curl. Okay? So the curl and divergence is kind of a big deal now. And then we kind of seen the curl already, right? In Green's theorem. Now we're going to build this up into 3D case, which is known as Stokes' theorem. One more little thing is there's a thing called the Laplace operator. Laplace operator is this of some function. I mean, it's not good. Our book does not use it, but our book uses more of a physics notation, which is this. Second derivative. But which one? Which one do we mean, right? So this later in mathematics is a big deal, this Laplace's equation. So I want you to know both. This means divergent of a gradient. Divergent of gradient of f. Okay, and let's take and in our notation, this is divergent, right? Dot product. This is what we mean by del square. But there are many mathematicians who hate this like dot product with a del, so that's like they actually physically spell out the divergent. Okay, now let's take it and see what it is. So that del dot, and then this thingy becomes partial f partial x I vector plus partial f partial y j vector plus partial f and partial z k vector is what we get. Actually, I'm going to spell this thing out too. And this thingy, remember, was partial x, let's put I vector here, plus partial j vector first, partial with respect to y, plus, why do I never give myself enough room when I do these things? And then k vector, good. And we dot these things. So when we dot it, this thingy and this thingy, so what we end up is second derivative. And no I, we are just adding them up. This is, so it's just an ordinary, or some people like it this way, fxx plus fyy plus fzz. So it's exactly what you want it to be. Okay, just take a second derivative of all of these things and then add them up. So this is known as the Laplace operator, which is really the second derivative with respect to spatial variable, they say. Okay? And it looks easy, but it's a little more complicated than you think. Okay? Now, any questions?
I think you forgot a squared for the d squared f over dz squared.
Oh my God, nice catch. There. Okay, anybody else?